Hey guys, okay, so today we are going to start Unit 3. Now, Unit 3 is all about light, electron configurations, and periodic trends. So we're going to talk about electrons and how they behave, but before we can talk about electrons and how they behave, we have to talk about light because they're pretty intertwined. We're going to talk about how electrons are organized within the electron cloud. And we're going to talk about periodic trends for this unit. Now, just a little reminder, there's always a calendar on the front of the notes if you ever need to know when something is or what we're doing that day. And it's also on Canvas along with video notes if you missed a day or if you want to review. Okay, so we're going to start with light. Now, light is kind of weird. Okay, light can behave as a continuous wave or a photon, which is a particle. So basically what light does is that it's, I guess the best way to describe it, it's a stream of particles traveling in a wave. And so it has properties of both a particle and a wave. Now, we call this is called the wave-particle duality of light. So that means that light, like I said, could be described as a wave or a particle. Now, for calculation purposes, when we're calculating waves or wavelengths or the speed of light or whatever, we tend to use the wave model. Okay, we tend to use the wave model. The particle model, the photon model is a little different, and so we're just going to look at the variables of a wave. Now, first, let's talk about how waves are measured. They're measured using wavelength and frequency. Now, the wavelength is the distance of one complete wave cycle. Okay, one complete wave cycle. So, the wavelength is how far apart either crests or troughs are in a wave. Now, there's this whole spectrum. We're going to talk about it. It's called the electromagnetic spectrum. And there's only a certain wavelength that humans can see. And we see it as color. Okay? And those wavelengths, the wavelengths that are visible to humans, are 700 nanometers to 400 nanometers. Now, wavelengths are measured in, it can be anywhere from micrometers to nanometers, or sorry, to meters, just depending on what type of wave you're looking at. So we're going to look at the different waves in a little bit, just kind of what those look like. But just know that the wavelength that's visible to humans is 700 nanometers to 400 nanometers. Now, the symbol for wavelength is kind of weird. It's this, I kind of describe it as an upside down, or upside down Y, okay? And so anytime you see this symbol, that's going to be describing wavelength. Now, the units for wavelength are meters and nanometers, so like I said, but they can go to incredibly small wavelengths all the way to very large wavelengths. Now, for our drawing, we're going to draw a wave, okay, and we're going to show that the distance between the crests, okay, the distance between the crests or the troughs is going to be our wavelength, okay. So the crest is the one where it goes up, so that's called a crest. Okay, And then the trough is kind of the part where it's going down. Okay. Trough, think of like a feeding trough for an animal. Now, frequency is the number of wave cycles. Okay, so this is a wave cycle. It's the number of wave cycles that pass a certain point per second. Okay, so it's the number of waves that pass a certain point per second. So here we have 3 examples. This is all within 1 second. So here we see that only about 4 cycles per second pass this length, okay, or past a certain point. Now here we have 16 cycles per second. So what's happening, if you'll notice that as wavelength is decreasing, our frequency, how many cycles can pass per second, is increasing. And so one thing we're going to emphasize is that as wavelength decreases, frequency increases. So frequency symbol is just a V, okay? And the units for frequency is 1 per second, okay, or 1 over second, or another way of saying is second to the -1. Anything that's raised to the -1 means 1 over. Or another way of measuring or the units of frequency is going to be hertz. Okay, frequency is measured in hertz. Also, so if you look down here, it says 16 cycles per second equals 16 hertz. Okay, so those are the 2 different units we're going to use for frequency. Now let's talk about the speed of light. Okay, the speed of light, we always have heard the term of like traveling in the speed of light, or if we can surpass the speed of light, but let's actually talk about what that means. So all types of electromagnetic, radiation waves travel at the same speed. Okay, so all forms of electromagnetic radiation travel at the same speed. Now they are going to have different wavelengths and different frequencies, but they will all travel at the same speed, and this is the speed of light. Now the symbol for the speed of light is a C, and the speed of light, so the speed of light is going to equal 3.0 times 10 to the 8th meters per second. So that means in 1 second, light can travel 3 times 10 to the 8th. Now, that is, or 10 to the 8th meters. Now, that is incredibly fast, okay? Very fast. That would require a lot of energy to actually travel at the speed of light. And so we have not yet been able to achieve that, okay? Now, the energy of light is the amount of power of a wave, okay? So it's how much power a wave will have, an electromagnetic energy wave. Now our symbol is going to be E for energy, and energy is going to be measured in joules. Okay, joules is the unit of measurement that we use for energy. Now let's talk about the different forms of light. Okay, now like I said, light, the visible light spectrum is from 700 nanometers to 400 nanometers. Okay, now remember, these nanometers are measuring wavelength. Okay, so we have 700 nanometers, that's what we see as the color red, and 400 nanometers is what we see as the color violet or purple. Okay, now this is a very, very small fraction of the actual electromagnetic spectrum. okay? And so what you'll see is that on our left end of the electromagnetic spectrum, we have radio waves. This is 10 to the second. What that's measured in is meters. Okay, so all of these wavelengths are measured in meters. Okay, and so here we have 10 to the second meters. So it's about like 100 meters. Now, radio waves can be really, really big. They can actually get to be the size of the Earth itself, especially in space. But when you think of radio waves, you probably think of FM and AM radio waves. Those can travel across long distances just because they are so big. And then we have microwaves. Okay, microwaves is 10 to the negative second meters. Microwaves, we use microwaves. You may think of a microwave oven to heat things. So those are actually bigger than what we can see. Then we have infrared. Infrared is what we use that's what we use to see night vision. Okay, and a lot of animals can see in infrared. Then we have our visible light spectrum. And then after that we have ultraviolet. So those are those UV rays. Now anything that's going to be on this side, on the right side here, is going to start becoming more and more harmful. That's because their wavelengths are starting to get less or smaller, and that means that their frequency is starting to increase. Okay, it's going to be a higher frequency. So the wavelengths are smaller, higher frequency. Therefore, they have a higher energy. Okay, and so what's going to happen is this UV rays, this is what gives you a sunburn, okay, from the sun. So you spend too much time out in the sun, you're exposed to these UV rays for a long time, and they can be damaging to your skin. Then we have X-rays. X-rays are even more damaging. Okay, X-rays, when you take an X-ray, you have to wear that iron vest, right? Or that, not iron, it's lead. So you have to wear a lead vest to cover your organs, your internal organs. Now, short exposure to X-rays is not too bad. I mean, if you're getting an X-ray and you're in there, you don't have to be too concerned about it because you're not going to be exposed to them for very long. But long exposure to X-rays can be damaging. And then we have gamma rays, okay? Gamma rays, gamma radiation. We talked about gamma radiation when we were talking about nuclear reactions. Gamma radiation is incredibly harmful, okay? It causes cancer. It does not cause you to become the Hulk, so don't even try it. So gamma radiation is the most harmful, okay? So one thing to kind of remember this order of our electromagnetic spectrum is we can do a kind of a helpful way of remembering this is think red men in Virginia use X-ray guns. Okay? Red men in Virginia use X-ray guns. So that means we have radio waves and then microwaves and then infrared and then visible light and then ultraviolet light and then X-rays and then gamma radiation. So red men in Virginia use X-ray guns. Okay, so this is a good way to kind of remember it in order. Now, again, let's talk about the relationship between wavelength, frequency, and energy. Okay, so over here in radio waves, we have a really large wavelength, okay? So this is a large wavelength. Well, if your wavelength is larger, that means that your frequency is going to be less. You're going to have a lower frequency. So remember this example over here. We had a larger wavelength. Therefore a lower frequency, 4 cycles. Here we had a smaller wavelength and a higher frequency. Okay, so on the radio wave side, we have a higher wavelength, a lower frequency, which means we're going to have a lower energy. Okay? Now, on the gamma radiation side, we have a very small wavelength. Okay? That wavelength is 10 to the negative 12. That's a very small wavelength, and that's meters. That means we're going to have a very low frequency. We're not going to have a very low frequency. We're going to have a very high frequency. Okay? Smaller wavelength, higher frequency means higher energy. Okay? So it says, what relationship do you notice between wavelength and frequency? Okay? Wavelength and frequency. So as wavelength increases, frequency is going to decrease. That's what we call an inverse relationship. They're opposite of each other. Now, it says, what relationship do you notice between frequency and energy? If you have a higher frequency, you're going to have a higher energy. So that is going to be called a direct relationship. Okay? Then it says, what relationship do you notice between wavelength and energy? Well, as wavelength increases, energy is going to decrease. Okay? So looking up here, our radio waves have the least amount of energy because they have the highest wavelength. That's why they're not damaging to us. Okay? It starts to get damaging here as we decrease our wavelength. We're starting to get more damaging radiation, and that's because our wavelength is smaller. That means our energy is much bigger. Okay? So this is an inverse relationship, okay, between wavelength and energy. So as your wavelength decreases, your energy is going to decrease. Now, let's talk about some calculations with light, okay? So we have a lot of formulas that we can use to calculate light waves. So our first formula is C, which is the speed of light, is equal to wavelength times frequency, okay? So the speed of light is equal to the wavelength times the frequency. Our energy, so if we're calculating energy, energy is equal to H, which H is something called Planck's constant, okay? Planck's constant, if you look at the last one, is 6.63 times 10 to the negative 34th, and that is joules seconds. Okay, this is Planck's constant. Now, I think it was Planck's constant that, was that what they had to figure out in Stranger Things Season 3? I think that's what it was. And then also energy equals Planck's constant times frequency. Okay. Then we have energy equals, also going to equal Planck's constant times the speed of light over wavelength, okay? Because if frequency, or if the speed of light is equal to wavelength times frequency, then frequency is equal to the speed of light divided by wavelength. And so if energy is equal to Planck's constant times frequency, then we can say that energy is equal to Planck's constant times the speed of light divided by wavelength, okay? Now again, the speed of light is going to be 3 times 10 to the 8th meters per second. Okay, that's the speed of light. Okay, so let's look at some examples of this. Our first one says, if the wavelength of light is known to be 5.5 times 10 to the negative 7th meters, what is the frequency? Okay, so we were given wavelength, okay? Our wavelength of light is equal to 5.5 times 10 to the negative 7th meters. We're trying to find frequency. Now, looking up at our formulas, we have to find the formula that has wavelength and frequency and the speed of light, okay? So we're looking at all of those. Okay, so we have to look for the formula that has wavelength and frequency. Now, this one has wavelength but not frequency. This one has frequency but not wavelength. But also these have energy, and we aren't talking anything about energy. So we're going to be using the speed of light equation. because we know that the speed of light is 3 times 10 to the 8th. So we're going to say the speed of light is equal to wavelength times frequency. Now, but if we're trying to find frequency, frequency is equal to the speed of light divided by wavelength. Okay, so we're going to plug in our variables. Frequency is equal to the speed of light, which is 3 times 10 to the 8th meters per second, divided by wavelength, which is 5.5 times 10 to the negative 7th meters. Okay, now notice, remember frequency's unit is 1 over seconds, and so what's going to happen is these meters are going to cancel out, and you're going to end up with 1 over second. So when we divide these, we get 5.5 times 10 to the 14th hertz, which is a unit, or 1 over seconds, or seconds to the negative 1. Okay, so that is our frequency. Okay, this is a pretty high frequency, but look at our wavelength. Our wavelength is pretty tiny. So next example, it says if the frequency of light is known to be 9.5 times 10 to the 14th seconds to the negative 1, so frequency is 9.45 times 10 to the 14th seconds to the negative 1, would the light be visible? Okay, if not, would you predict it to be UV or IR? Okay, so in order to figure out the visibility of light, we actually need to find the wavelength, because that's what our electromagnetic spectrum is given in wavelengths. And so, again, we're going to use our formula. Speed of light is equal to wavelength times frequency, but this time we're trying to find wavelength. So wavelength is going to equal speed of light divided by frequency. Okay, so wavelength is equal to our speed of light, which is 3 times 10 to the 8th meters per second, divided by frequency, which is 9.45 times 10 to the 14th seconds to the negative 1. And what you get is 3.17 times 10 to the negative 7th. Okay, and this is meters. Now, when we look at our visible light spectrum, our exponent is 10 to the negative 7th, okay? And so if you notice, our exponent here is 10 to the negative 8th, and so it's probably going to fall right here, so it's really not going to be visible. So that it is not visible. Okay, it's UV because the wavelength is smaller than 400 nanometers, okay? So this would be 3.17, or would it be? It would be 0.317 nanometers, okay? So it's smaller. Actually, no, it's 3.17, because remember, visible light is 700 nanometers, that's why I got it confused, to 400 nanometers, which is 7 times 10 to the negative 7th meters to 4 times 10 to the negative 7th meters, okay? And this is going to be 3.17. Why did I put that as negative? Oh, that's 2. This is going to be 3.17 times 10 to the negative 7th meters. Okay. Now, our next example, it says, what is the wavelength in meters of the electromagnetic carrier wave transmitted by a radio station at the frequency of 640 kilohertz? Okay, this is a kilohertz. Okay. So we can, we're trying to find wavelength, and we're given frequency. So we can use the speed of light equation. Speed of light equals wavelength times frequency. So trying to find the wavelength is going to be equal the speed of light divided by the frequency. But what we have to do is we actually have to convert the kilohertz into hertz before we can actually solve. Okay? So 640 kilohertz. Okay, 1 kilohertz is going to be 1,000 hertz. Okay, and so we get it's actually 6.40 times 10 to the 5th hertz. Okay, so we have to convert kilohertz to hertz before we can plug it into our equation. So wavelength is 3 times 10 to the 8th meters per second divided by 6.40 times 10 to the 5th hertz. And so that's going to give me 470 meters, or 4.7 times 10 to the 2nd meters. Okay, so that's how big the wavelength. That's a pretty big wavelength, 470 meters. Think about that. Now the next example is, what is the energy of a photon of light whose frequency is 7.85 times 10 to the 15th hertz? Okay, so in this case we're looking for energy, okay, and we're given frequency. So we're going to use our equation. Energy is equal to Planck's constant times frequency. Okay, so energy is going to be equal to 6.63 times 10 to the negative 34th. That 6.63 times 10 to the negative 34th is Planck's constant. That's H. Our units is going to be joules seconds. Times 7.85 times 10 to the 15th hertz. Okay, that's our frequency. And so our energy is going to equal 5.20 times 10 to the negative 18th joules. Okay. So that will be our energy in joules for this frequency. Now, the next example says if one photon of light is known to have an energy of 3.33 times 10 to the negative 19 joules, is the light visible? Okay, so we need to find, in order to find if the light's visible, we got to find wavelength, okay? So we know that energy, we're given energy, so we got to use one of those energy equations. And instead of using this one with the frequency, what I can use, since I'm trying to find wavelength, is I can use energy is equal to Planck's constant times the speed of light divided by wavelength. And when I solve for wavelength, wavelength is going to equal Planck's constant times the speed of light over energy. Okay? So our wavelength is going to equal Planck's constant, which is 6.63 times 10 to the negative 34th joules seconds, times the speed of light, which is 3.0 times 10 to the 8th meters per second, divided by our energy, which is given in our answer, or in our question, is 3.33 times 10 to the negative 19th joules. Okay, so when we solve this, when we solve for wavelength, we'll get 5.97 times 10 to the negative 7th. Okay, so that's 597 nanometers. Okay, so remember, visible light is between 700 nanometers, which is 7 times 10 to the negative 7th meters, to 400 nanometers, which is 4 times 10 to the negative 7th meters. So yes, this is, yes, it is visible. Because it falls in between those two. Okay. Now the last one, it says if a light has a wavelength of 6.6 times 10 to the negative 7th meters, what is the energy of one photon of this light? Okay. So what we're trying to find, what energy actually describes is the energy of the photon. So remember, light is that particle duality, so that particle wave duality. And so what we're trying to find here is the energy of that light, okay? And we're given wavelength. So we're going to use the formula E equals Planck's constant times the speed of light divided by wavelength. And so I can just plug it in. I don't have to rearrange it. So energy equals Planck's constant, which is 6.63 times 10 to the negative 34th joules seconds times the speed of light divided by 3.33 times 10 to the negative 19th joules. Okay, so my energy is going to equal 3.01 times 10 to the negative 19th joules. Okay, oops, I did 19 right here. Whoa, what did I put here? I was looking all over the place. What now? This is actually 6.6 times 10 to the negative 7th meters. I was looking all over the place. So our energy is 3.01 times 10 to the negative 19th joules for this wavelength. Now, looking at this wavelength, let me ask you this. Is this wavelength on the visible light spectrum? And the answer is yes, because it's in between our two nanometers. Okay, so this is probably kind of a reddish orange maybe on the visible light spectrum because it's closer to 700, which is red. Okay, so these are just the different formulas for light and describing the behavior of light. And this is important because our electrons do this weird thing by jumping energy levels, and they emit light when they do that. And so this energy of the light is going to be related to electrons' energy levels.